So, hi everyone. By now, I'm hoping that you will have already looked over the slides that I posted on Moodle that are entitled Welcome to Regression. So, I want you to look over those slides. It's a really good general background as to why it is we need to use regression, why we need to add regression to our biostats toolbox. And so, after you've looked at those slides, please come back here and take a look at some of the demo videos. This is just the intro video because I wanted to introduce you to logistic regression. And so with logistic regression, we're going to actually go back and use the same data that we've used before, the cosmetic surgery data set. Obviously, we've used it before, but it is a good one and it has several variables in there. And I'll show you throughout these videos and throughout this demo how to use these variables in a regression model. So why do we really need regression? It really comes down to the fact that when we're looking at a relationship between a specific exposure and a specific outcome, there are all of these other confounders or these extraneous variables that also have something to do with that relationship. And so we need to be able to take those into consideration in our statistical models. So for this lab, we're going to be looking at binary logistic regression. And so this is the statistical method that we use to summarize the relationship between a dichotomous dependent variable. So this means that our dependent variable or our outcome has two levels, a yes, no, heart attack, yes, no, pregnant, yes, no, smoking, yes, no. However your outcome is arranged, it has to only have two levels to the variable. And then we're going to look at one or more explanatory variables. So those are our independent variables. Again, that would be our exposure of interest, but then also perhaps several confounders as well. So I have an example here that has nothing to do with the cosmetic surgery, that has nothing to do with the Burfis data set, but does link back to the slides that you've just looked at in the Welcome to Regression slide set. So is there a statistically significant association between smoking during pregnancy and income? And that's categorized as above or below $50,000 per year, while accounting for differences in education, marital status, and maternal age. So here you can see that we have smoking during pregnancy and income are our two variables of interest, right? So both of those can be categorized dichotomously, which is great, but then we're also going to be accounting for several confounders in this relationship. The differences between education, marital status, and maternal age are in fact our confounders. So this would be our research question of interest. So the next step that we would have to do is construct our skeleton table. So I've done this down here, and again, this has nothing to do with Burfis. This has nothing to do with cosmetic surgery. This example is linking back to the Welcome to Regression slides. So here you can see that we're going to be doing a binary logistic regression model for smoking during pregnancy. So because smoking during pregnancy is our outcome of interest, we're going to have the constant for smoking during pregnancy here. And we're going to be able to list both a beta and a standard error. That's what this B and SE stand for. And then also an odds ratio and a 95% confidence interval. Now, these two things should be pretty familiar to us because we've talked about this type of measure of association earlier on in the semester. And here what we're going to do is we're going to look at our main exposure of interest, so this income above or below $50,000 a year, while taking into account education, marital status, and maternal age. These three things listed down here will be our confounders. So I wanted to reiterate this because it's a really important point. Binary logistic regression is my favorite of the two regressions that we're going to learn because the way that you interpret an odds ratio for me is more intuitive than how you interpret a beta. So I just want to go through again how we look at odds ratios and then what that means for our measure of association. So when your OR or your odds ratio equals 1, that means that there is no association between your exposure exposure and your outcome. And when you are also including confounders in your regression model, that means that there is no association while holding all other confounders constant. So when your odds ratio is greater than 1, that means that as the predictor increases, so as the exposure increases, the odds of the outcome occurring also increases. So the very easy example to think of when we think of this is as smoking increases, your risk of lung cancer also increases. When we think about risk factors, we usually think about things that are bad or harm us in some way, that we're more likely to get a disease because we do it. Now, there is also another side of the odds ratio, and that's when the odds ratio is less than 1. And that means as the predictor increases, the odds of the occurring actually decrease. So this would mean that the risk factor itself is actually protective. So if we think about if we get a vaccine, for example, the more vaccine we get, the less likely it is that we are going to get the disease. Or whether or not we get the vaccine means that we're less likely to get the disease. And because I am a very visual person, I also wanted to give you guys a Professor George original artistic drawing here of odds ratios. But this is the idea of an odds ratio being 1. And if it crosses this line, that means that there is no association between the exposure and the outcome. But if we go below 1, so something that's less than 1, we're thinking about a decreased odds of the outcome. And then when we cross over this side, we're thinking about an increased odds of the outcome. And over here, I just have a couple of examples. And I've also included the 95% confidence interval in a visual way here as well. So I'm going to start down below here. If our odds ratio, let's say, is 1.3, and we have a 95% confidence interval that is inclusive of that null value, that odds ratio of 1, meaning we have a range of 0.8 to 3.1, that means that there is no association, that there is no statistical association between our outcome and our exposure. However, over here, this is a visual representation of some type of exposure that's actually protective. Because here, let's say we have our measure of association is 0.5, and our 95% confidence interval here is 0.8 to 0.03, which means we do not cross this null value. So this 95% confidence interval is showing us that we do have a statistically significant association between our exposure, which is protective in this case, and our outcome. Sorry about that, guys. So the other thing that I wanted to talk about here is a increased odds. So for example, here, let's say our measure of association is 2.1. And I'm just choosing a number in between our 95% confidence interval here. So we have a 95% confidence interval range that goes from 1.4 to 5.6. And that means because this does not contain the null value of 1, that this is a statistically significant association between exposure and outcome for an increased odds of the disease. So now that we know how to interpret odds ratios, let's switch gears and think about our cosmetic surgery data set. So forever and always, the first step in doing anything in SPSS is actually not to go to SPSS, but to think about what our research question of interest is, sort of outside the realm of needing to worry about which keys to hit. So the question that we want to ask here is, does gender predict whether someone is depressed or not? So we've done this before. We've actually looked at males and females in the cosmetic surgery data set, and we did find that there was a difference between gender when it came to depression. So just to jog your memory, I'm going to bring you back to our cosmetic data set here. And remember here we had gender, 0 being female and 1 being male. And then we also had BDI, or this is the Beck's Depression Scale. So these are the two variables that we want to think about in this research question of interest. So what we want to do here is expand this beyond just the biostats tools that we have in our toolbox. What we want to do now is we want to think about gender and reason for surgery to predict whether or not somebody is depressed. So if we go back here to cosmetic surgery, we're now going to be incorporating this variable right here. So this is if we expand this here, we can read that this is the reason that somebody decided to get cosmetic surgery. And here we can see that there are two reasons that somebody might have decided to get cosmetic surgery. Usually either that they wanted to change their appearance, or there was some type of a physical reason, like they got in a car accident or something along those lines. So those would be the two reasons that we have in this data set. So if we go back to our research question of interest, we want to first, of course, build our skeleton table. So this is what a simple logistic regression skeleton table is going to look like. You're going to always have a constant, and that constant is going to be available for you to record the beta, the standard error, the odds ratio, and the 95% confidence interval for depression. That's really what your constant is going to be representing. And then you're going to have your main predictor of interest, which in this case is gender. But then we also have a confounder. We think that also reason that somebody had decided to get cosmetic surgery might also be associated with depression. So we want to also include this variable in our logistic regression model. So to make sure that we can use logistic regression, we have to make sure that our variables are the proper format in order to build our model. So for model 1, does gender predict whether someone is depressed or not? Our dependent variable or our outcome needs to be depression. And it can't be in the format that it currently is in, because right now Beck's Depression Inventory is a continuous variable. So we're going to have to come back to this and we're going to have to transform that variable. But let's check on gender. So the predictor, or the independent variable here, is gender, and it needs to be set as male or female. And we already know that that is in fact the case. So for model 1, all we need to do is make sure that depression is categorized into a dichotomous variable as opposed to a continuous one. And if we go down to our model 2, so our second research question of interest, again, we need to make sure that depression is in fact dichotomized into yes or no. And we've already checked that gender is male, female, and then we just did check in the last video that reason for getting cosmetic surgery is either a change in their appearance or for some type of physical reason. So again, in order to run this logistic regression analysis in the data set, we need to make sure that our depression variable is in fact dichotomous. So what I'm going to do here is something that you guys are very familiar with, but we're going to go up to transform. We're going to recode into a different variable, and we're going to take this Beck's Depression Inventory, and we're going to change this into a dichotomous variable here. So you can just say depression, yes, no, something along those lines. Oops, we're not allowed to use a slash. So we're going to say yes or no. That should be better. Oh, I think it's actually a space up here. Okay, change. There we go. Sorry about that. Make sure that you don't have a space at the end of it. That was my mistake. So we want to make sure that you don't have a space, or else that's going to be an illegal character for your variable. So then you want to go to old new values, and here what we want to do is we want to set a midpoint. So we want our range to be from the lowest value of the depression inventory, and I forget what it is, but we want it to code all the way up to 19.9. So you want to say 19.9 here, and you want that value to be a 0. Okay, and then the second value, again, we're just making two levels. We want this to be a dichotomous outcome. The highest, or the range is from 20.0 through the highest value that exists, and we want that to be a 1. Now, remember when we were doing this either back in Lab 2 or Lab 3 demo, I said it really didn't matter how you coded these, whether it be 1, 2, or 2, 1, or 0, 1. Now it actually does matter, and you want to make sure that the non-risk variable, so the lower depression, is also the lower value as well. It's going to come into handy when we think about interpreting our odds ratios. We need to make sure that our outcome is set up like this. So you want the non-risk variable to be the lower number and the riskier variable to be the higher number. Whether it's 1, 2, or 0, 1 doesn't matter, but it does matter that this is the lower number and that this is the higher number. So we're going to go ahead and say continue and say okay. So here's our output saying that we did in fact execute that. And here we should see that we have our new dichotomous BDI. And just before I forget how we did that, I made the 0 to be low depression, and we made the 1 to be a high depression. I always like to do this right away because I'm super forgetful and I don't want to forget how I categorized things. So now if we go ahead and go back to our demo, we can see here that we have this coded the proper way. So our step 2 is now complete. Okay, I'm going to take you through step 3 and step 4 in the demo, and then I'm going to take you over to SPSS and show you that. But when you have a categorical predictor, so if you're either your exposure or your confounder variables are predictors, you have to tell SPSS which direction you would like the predictors to compare to each other. So for example, here gender is going to be in our first block or our first regression analysis, and we need to tell SPSS that 0 is the female variable and 1 is the male, and that we actually want the first indicator or female to be our reference group. So that's sort of the first window that we're going to have to go in and do. So if we go to cosmetic surgery here, we go up to analyze. We finally get to come down here to our regression. How exciting is this? Go to binary logistic regression. I've already done it here, so I'm going to just reset. This is what yours should look like here. We're going to pull depression into the dependent variable, and then we're going to pull gender into the block. And once we do that, you can see here that the categorical button becomes available for us to click. So pull gender over, it's already automatically going to say gender indicator, but what we want to say is that we want female, or the first level of the predictor variable, to be our indicator. So we're going to have to go ahead in and actually click change. And so you'll see now up here that our indicator, we want the first variable, so the 0 in the dichotomous variable of gender, to be our indicator. So go ahead and say continue. So now we're going to hop back to the demo here, and we're going to go down to step 4. What are the odds? So this is the exciting part where we're actually going to get a odds ratio as an output from our logistic regression. But as you can see here, we're going to have to click on options, and then we're going to have to tell SPSS that we actually do want a 95% confidence interval, and we want SPSS to calculate our odds ratio for us as well. So if we hop back here, we're going to go to the options setting, and we're going to click this button here for the confidence interval for the exponential beta, which is also known as the odds ratio. And again, we are going to leave it at the default for 95%. So go ahead and say continue and press OK. And here is our logistic regression output. So you can go through here and you want to actually just go scoot all the way to the bottom. I know these are a lot of numbers. Really all we're concerned with is the model summary here, and then the variables in the equation. The rest of the information that's up here is really more graduate level information, so we really don't have to worry about it. Again, model summary and then the equations in the variable are the two outputs that we're going to be spending our time looking at. So here we're back in our demo, and you can see here that step 5 is the output and how to read the output after we run our simple logistic regression model. What do we need to fill in our skeleton table? So I've screenshotted these two pieces of information from SPSS output and put it here in the demo. So this right here is telling us how much of the variability in our outcome does the model actually explain? And so if you move the decimal point over 2 here, you can see that if we just look at gender, gender is explaining 35% of the variability in depression. So if you think about it as an entire pie, a circle, the piece of the pie that gender is explaining is worth about 35% of that entire pie. So that's how you read the model summary up here. Now, if you go into the variables in the equation, we want to grab several numbers from this here. This is sort of where the meat of the matter is. We have the betas listed here. We have the standard errors listed here. And then here is where we have the exponent of the beta, which is also known as the odds ratio, as well as the confidence interval. So if we sort of take our table here with our simple logistic regression, you can see where I've put all of this information here. So you can see that this is the constant, the beta for the constant, and then also the standard error is here. You can also see that the gender, this is indicated as 1 here. So I know that that means male because I've gone in and I've looked at the SPSS data here in the data view, and you can see here that 1 actually equals male. So I know that the output, when it has the parentheses 1, is talking about the male category. And this is going to be important for how we analyze and interpret our findings. So we can see here that male is indicated by this beta and this standard error. And then we want to go over here and actually also capture the odds ratio and the 95% confidence interval. Now also you can see here that I've grabbed the R squared, and this comes from this up here in the model summary explaining 35% of the total model. So it's a 0.35 in terms of the model fit. Now when we're coming down here also, I just had a sort of a general rule, sort of a general note here. When we're looking at just a simple logistic regression, so we have just the outcome and one predictor. If there is a p-value or a confidence interval that is around the level of 0.20, so this is not statistically significant technically, but it is trending in the direction of statistical significance. So it's not at the 0.05 level, it's at the 0.2 level. Usually epidemiologists and biostatisticians will think that, well, if we have a low enough p-value, and that low enough is that at that 0.2 level, that it will follow into using it in the multivariate model. But here you can see that our constant is in fact statistically significant, so we do have a very small p-value, so we would carry through gender regardless. And you can also see that because our 95% confidence interval does not cross the null value of 1, that this is also telling us that we are statistically significant and we should carry gender through because there is something going on between depression and gender. So now what we want to do is we actually want to go back to our second research question of interest. And that one had to do with not only looking at gender, but we also wanted to include our confounder, which was reason for getting cosmetic surgery. So we can, again, do this in a multivariate logistic regression model. So what we want to do is we want to go back to our cosmetic surgery. Again, we're going to go down to regression, binary logistic, and we should actually see that we have our last model set up. If we want to keep this model and basically rerun it, what we can do is we can, oops, didn't want to do that. What we can do is we can add a second block. So this second block is basically going to run two logistic regression models at the same time and actually compare and see which one is better. So in this second one, we want to make sure that we're including our confounder as well. So we already know that this is categorical. We told it that we wanted female to be first. So SPSS remembers that, but this is the first time that SPSS is seeing reason. So we do want to go in there and tell them that reason is also a categorical variable. And I always like to make sure that our first level is in fact the indicator. It just makes more sense in my mind to keep it that way. So go ahead and do the same thing for reason. Now both of those are indicated as a categorical variable in our second block. You can go to options. It still should be checked for 95% confidence interval and to take the exponent of the beta for us. So we can go ahead and just say okay again. And we're going to run a second logistic regression model. And again, there's a lot of information here. This is block 1, so this is the first time that we ran the model, should be exactly the same, but now we have some more information because this is block 2. So block 2, we want to look at the model summary again, as well as the variables in the equation. So I believe I've just screenshotted that for you. And we can look at this now. So here is our model summary, and you can see here that our R squared is much larger, meaning that when we take both the reason for getting cosmetic surgery as well as gender, and we put both of those pieces into the entire pie of trying to explain the variability in depression, that we're actually explaining 62% of the variability in depression with using both of those variables. So just there, we know that we're explaining more of the variation. So we think that depression actually has to do with both of those two variables. But down here, we can see as well that we're going to have a beta, a standard error for not just gender, but also reason for surgery. And of course, always our constant is there as well. Because we have a new variable in our model, you can see that the beta for both gender and constant is changing due to the fact that we're including reason for surgery in our model. And here you can see that we have both the odds ratios and then also the upper and the lower 95% confidence interval for block 2. So again, I've just written this out here for you. Model 1 is explaining about 35% of the pie, whereas Model 2 is explaining 62% of the pie. So by adding reason for getting cosmetic surgery, we're actually improving our model fit. That's my opinion, and it's also we can back it up by looking at SPSS as well. So this is another screenshot of one of the outputs that you're going to see when you have two models set up in two different blocks of the logistic regression models. And you can see here that statistically significantly there was an improvement between block 1 and block 2. And we see that here because this p-value is statistically significant. It's basically doing a chi-square test. So this is the entire test statistic and the p-value, which means block 2 is probably the better model to explain depression. So what I did here is I just have a table 2 for you. You can go ahead and fill this in. The constant should be different, and then also the beta and the standard error for gender should be different because now we also have a reason for doing cosmetic surgery in our logistic regression model. And we're going to want to use the block 2 model fit here, which is going to be closer to 62%. So once you fill in the numbers here, this is a way that you can actually interpret the outcome here. This is actually really important. The 7th step of logistic regression is our last step, but it is probably the most important. So once you find the final model that fits your data the best that you possibly can, the way that we would interpret this is, on average, men had a 0.11 times the odds, because again, we're using an odds ratio here, of being depressed as compared to females. And we also want to use the 95% confidence interval because this is telling us not only that it is statistically significant, but also giving us the entire range of the 95% confidence interval here. And of course, this is after we controlled for the reason for getting cosmetic surgery. So we're holding this constant and just looking at the difference between gender and depression. So because the confidence interval does not contain the null value of 1, we are able to reject the null hypothesis. The other thing that I want you to include when you're talking about your logistic regression output is I want you to tell me how much of the model you are able to explain. And so again, because, going back up here, because our R squared is 0.624, we're explaining approximately 62 of the variation in the data.